hope you didn't miss anything important. You probably didn't. So this is me down here. I'm an assistant professor in the Department of Biological and Environmental and Engineering at Cornell, but I just highlighted my name to show you who I am. This work has been a collaboration with Farshid Salimijazi, my first ever graduate student who's in the audience and is giving a poster. Jaewon Kim, who was a senior at Princeton who helped me out with this work. Alexa Schmitz, my first postdoc. And Andy Bakarsley, a chemist in Princeton's chemistry department who works on the electrochemical reduction of CO2. And Farshid insisted I put this QR code up to link to his latest paper. So my lab's thesis, put it simply, is that over the past 80 years or so, applied biology has revolutionized medicine. So think antibiotics, vaccines. And our thesis is that over the next 80, applied biology could revolutionize sustainable energy. Why do I think this? Me and Jose Avalos, a collaborator at Princeton, put together this Venn diagram that shows all of the capabilities of biology that we think could be used to solve problems in energy. So you start out with some of the most fundamental, like room temperature, room pressure catalysis, self-assembly. And these support things like self-repair and replication that could make biologically based energy systems really cheap. Room temperature, room pressure, light capture and CO2 fixation, redox transformation, materials synthesis, the list goes on. And this could be used to solve all sorts of problems in energy. Biofuels, at least in my mind, are probably the most obvious, but they're certainly not the only one. Advanced material synthesis, the mining and purification of rare earth elements that we need for advanced electronics, making battery electrodes, enhanced photosynthesis. And then there's a whole set of problems that really require redox transformation. There's nuclear sequestration and remediation, nuclear fuel mining, battery electrode recycling, maintenance. And then last, the one that we're most interested in is artificial photosynthesis. And this is a class of problem that electroactive microbes that can interchange electricity with their environment, either directly or through intermediates like hydrogen, specialize in. So I bring up artificial photosynthesis, and it's related to this challenge of energy storage. So right now, yesterday Jerry Woodall quoted the same number, and I was so excited we were right. The installed US electrical energy storage capacity on the grid, if you discount EVs, is about 1 gigawatt hour, which is 0.0036 petajoules. Worldwide, that stands at about 20 gigawatt hours. And these sound like a lot of power, right? It's got a giga in front of it. But how much energy storage will be required, especially for a sort of future sustainable energy infrastructure? So in a recent paper, Farshid, and here's a link to it, looked at a range of energy storage scenarios for the future world. So we listed them out here. We looked through the literature and we listed them out here. And we are the energy storage requirements go from a ballpark low estimate for the EU or US for a grid that has about 80% renewables. And you might think this needs about 1 petajoule of storage. If you go down here, as you increase the fraction of renewables on the grid, especially as you go closer and closer to 100%, the storage requirements rise exponentially. So if we go to 100% renewables, we'll need between 6 and 21 petajoules of storage. And 900 is the sort of upper end estimate. There's not a whole lot of agreement on this number, but we sort of have to think worst case scenario. Now, if we extend this logic to the rest of the world, this energy storage requirement only grows and grows and grows. And if we extend it to a future world in which more and more people want an American lifestyle, this energy storage requirement goes through the roof, up to even 26,000 petajoules or 25 exajoules of storage. What does this do to materials requirements? So we went ahead, and just to illustrate the challenge, this is not to say this couldn't be done with alternative battery chemistries, but we wanted to just illustrate the difficulty of the challenge of energy storage. We calculated out the mass, the theoretical minimum mass of lithium to make lithium-ion batteries to store all this energy. And then we calculated this as a fraction of the world reserve of these elements. And we also did the same for zinc manganese alkaline batteries. And it turns out, for Europe and the US, current world supplies of lithium could easily extend to building the required energy storage. It's when you extend this out to the whole world, and a world full of rich people, do we start to rapidly consume all the world's supply of lithium and zinc many, many times over. So materials availability challenges like this have really excited interest in energy storage systems that don't rely upon rarer elements, think like lithium, cobalt, zinc, and the like. And in this scheme, I'm showing what we call rewired carbon fixation schemes. There's a variety of names for this sort of system, and including electrosynthesis, think the bionic leaf from yesterday. I kind of like this phrase, but I'd be happy to choose one and stick with it if the community can. And you can imagine systems in which we have electrochemical water splitting that's powered by all sorts of renewable electricity. And we have coupling that with microbes that are able to absorb that electricity and then fix CO2 enzymatically, and then enzymatically convert that fixed carbon into an energy storage molecule. So think things like the bionic Dan Nocera and Pam Silver's bionic leaf. And then you can also imagine that there have been recent advances in the electrochemical synthesis of short-chain hydrocarbons like propanol, formic acid from CO2 at very, very high Faradaic efficiency up here. Andy Bacarsley, our collaborator, loves this sort of thing. And then you could couple this to microbes that don't fix carbon, but are really good at further reducing that lightly reduced carbon, like formic acid, to highly reduced molecules like butanol, octanol, C16. Now, how do we actually connect a microbe to an electrical power supply? And in this recent article, we pointed out 4 mechanisms. Hydrogen, of course, this one, you saw it yesterday, and it's definitely had the most success to date. It's probably the only successful one to date. So here it is. But there are a few others. Today, I'm just going to talk about extracellular electron transfer. So in this case, electroactive microbes like Shewanella or Geobacter, siderooxidans, can connect to a cathode through a secreted pilus called a nanowire and then transfer electrons at very high rates, either from metabolism to the electrode or from the electrode into metabolism. The great advantages of hydrogen are it works. It's got really well understood genetics, and the biophysics of it are well understood. But on the other hand, hydrogen has really low solubility in water. And it's also very volatile and explosive, and this leads to all sorts of potential problems on scale up. Nanowires have very, very high electron transfer rates, but the genetics are horrible, and the microbes are horrible to work with. They smell, and they're nowhere as easy to genetically manipulate even as Ralstonia, certainly nowhere close to E. coli, the workhorse organism for synthetic biology. And there have been very, very few, if any, actual demonstrations. The only one I can think of is an engineered strain of Geobacter from Derek Lovely's lab at UMass Amherst. The great thing about the bionic leaf is already, when it's been coupled to a solar PV, it exceeds the efficiency of photosynthesis. So I made this bar chart today. So here's the best in field C3 photosynthesis and the theoretical max, a little under 5%. Here's C4. Here the efficiency is about 6%, maximum theoretical. With algal photosynthesis, in bioreactors, you tend to do about 3%, but people think you could get up to about 9%. The bionic leaf, in the systems that were shown yesterday, it managed about 7% solar to fuel efficiency. If you were to replace the standard photovoltaic that it was coupled to with a perfectly efficient one, this would go up to almost about 13%. Now, having said all this, is that really enough? So, as Lee pointed out, biomass is dirt cheap. Jose Avalos and I figure that it costs between $2 and $4 to deliver a gigajoule of biomass to the farm gate. Saudi crude, just to get it to the top of the desert, costs $6 per gigajoule. It's the cheapest form of energy you can get. So any system that is going to supplant photosynthesis doesn't have to just exceed its efficiency. It's really got to blow it out of the water. So just how efficient could systems like the bionic leaf, rewired carbon fixation get? What's the way to get there? And which way is the most interesting, the most promising? So we've been looking at this in a paper that's upcoming, and I keep promising it'll be out next week, and I hope next week it really will. So we came up with this sort of theoretical framework to describe it. It's really simple. The efficiency is just the fuel generation rate by the energy density of the fuel on a per molecule basis divided by the power that you put in. And this, the input power is just the voltage across the electrochemical cell where you have your microbe multiplied by the current that goes through it. And then this voltage here, delta V cell, is the thermodynamic minimum of the difference between the half cell reactions on the anode and the cathode, this term here, delta V0, and then the additional bias voltage that you have to apply above and beyond that to actually make reactions happen. So for hydrogen, delta V0 is 1.23 volts. And then in ultra-low overpotential systems, you might find this is a little bit under a volt, but typically it's a bit over. So the fuel generation rate, and this is how we interface this framework with metabolism, is the amount of charge that's needed to synthesize a single fuel molecule from CO2 and multiplied by the fuel generation rate. And this is going to be less or equal to the cell current. And then, so the efficiency is no more than this equation down here. Now, we can then, let's turn to the molecular mechanisms of the system to come up with this term here, the sort of number of electrons you need to synthesize a fuel molecule. So we put together this diagram showing the internal mechanics of Ralstonia eutropha. So up here, hydrogen comes in at high energy, about negative 0.42 volts relative to standard hydrogen on a cathode. Down here, a soluble hydrogenase enzyme oxidizes the hydrogen and reduces NADH that can feed into biosynthetic reactions. We've also got a membrane-bound hydrogenase that also splits hydrogen, or oxidizes it, and then injects the electrons into the electron transport chain on the inner membrane. in doing that, it pumps protons across the inner membrane against this electrochemical voltage V membrane. And then eventually, those protons get pumped back into the cytosol, and they make ATP that goes into biosynthetic reactions. Here's a sort of an energy level diagram of it. You go from water up to hydrogen electrochemically. You roll a little bit down into energy in NADH, and then you roll a little bit further down in energy to your biofuel. People love hydrogen because this energy gap is very, very small. It's about 0.1 electron volts, which when you compare this with the thermodynamic minimum potential across the electrochemical cell is only about 7%. So it's a very small potential energy loss. So this is our equation for the number of electrons that you need to make a single molecule of fuel. It's the number of electrons you need to make the NADH that reduces CO2 to the fuel, plus the number of the number of ATPs, then multiplied by this rounding fraction that takes into account the fact that you can only pump integer numbers of protons either way through the inner membrane. And then you can plug into this numbers for this, and Farshid put together a table for this in our upcoming paper and also in an article that just came out. And you looked at a range of scenarios for different rewired carbon fixation systems with different carbon fixation pathways. These are for the Calvin-Benson cycle that the Ralstonia naturally uses. And then these are exotic carbon fixation cycles that you might find in thermophilic organisms. This one was computationally designed, called Ketch. And then this is the most efficient one we know, the Wood-Lundahl pathway. And he assembled the number of NADHs and the number of ATPs you need to get your final product, which is typically isopropanol. In this case, we made it isobutanol because the energetics work out a little bit better. And what you find is, here's the real bionic leaf in the lab. When you put these numbers in, there's a very slight gain to be had. We think it's actually very, very close to its theoretical limit in terms of performance. But how much better could you make this? If we go over here, the thermodynamic limit is from about 40%, it goes up to almost 70% conversion of electricity to fuel. Andy Bacarsley told me this is cheating. We can't just drop our bias voltages to 0. But this data here shows us a pathway. What we can do is by changing out this carbon fixation pathway, we can raise the efficiency of the system closer and closer and closer to that thermodynamic limit. And it gives us a roadmap to do this through biological engineering. Now, there's a problem with H2 that I alluded to. It's the solubility. And it typically means that we're going to have to stir. So we built this model. And this isn't to say this is an absolute lower limit on the energy you have to put in for stirring, but we think it's pretty close. If you have a 1 square meter solar PV, you make about 450 amps from that. And we think you need a volume of about 25 liters of cells at an optical density of 1 to deal with that, to fix all of the carbon that you could potentially use that to fix. Stirring that is going to need between 100 and 200 watts. That solar panel only produces 330 watts. So there's a potentially enormous efficiency hit. This is something you'd never consider in the lab. But out in the real world, that power has got to come from somewhere. And most probably your solar panel. So could you do away with that? And we think this is where nanowires might help. Right here, where we have an electrically conductive matrix that the bug secretes that could potentially move electrons at much lower energy. But to date, nobody's really figured out the genetics of this system. So knowing this a few years back, my lab came up with an experiment to figure this out. So the biggest challenge here is that we tend to pump in electrons into these systems at low energy, about 0 millivolts. But somehow they rise in energy to about negative 320 millivolts to reduce NADH. How does this happen? And what effect does this system have on efficiency? So my lab put together this system called Knockout Sudoku for systematically knocking out genes very, very cheaply in all sorts of organisms. The E. coli knockout collection and the yeast knockout collection cost about $3 million in 4 years to make. This system can do it for about $10,000 in a handful of weeks. We then made that Shewanella knockout collection, and we screened it with a redox dye screen for genes that eliminated electron uptake. And in doing that genetic screen, we came up with a list of candidates that we think affect this electron uptake process. So a lot of them are obvious, but we got some interesting hits. Some that interact with the quinone pool on the inner membrane. Some in this EET complex that transfers electrons from the outer to the inner membrane, and membrane-associated membrane proteins that we also think have a role in this electrical energy upconversion process. We've been collaborating with Annie Rowe and her technician Leah Trushell at the University of Cincinnati on electrochemical experiments to demonstrate these proteins really do have something to do with electron uptake. This is a picture of their electrochemical cell where they put our mutant Shewanella, and they've been able to find a handful of mutants that pass our screen and at the same time also can't absorb electrons on an electrode. And this gives us some confidence in a model that's, for how bugs like this uptake electrons. The idea is electrons come in at low energy, cross the EET complex here, and then as they come down to the inner membrane, some electrons are sent down to water at low energy, and then they pump protons. And that proton gradient can not only be used to make ATP, it can also be used to reduce NADH. Here's an energy level diagram for this. So electrons go down this way. Some go downhill, and then that energy is transferred to the uphill branch of this uphill pathway. This sounds really inefficient. But it turns out, when you actually do the math, it's not. It's actually comparably efficient to hydrogen, which really amazed us. So we've shown here some of the theoretical upper limits on the conversion of CO2 to butanol by several theoretical engineered organisms, one expressing the Calvin cycle, one expressing the 3-hydroxypropionate, 4-hydroxybutyrate cycle, and another one expressing the Wood-Lungdahl pathway. And they differ only in fractions of percent in terms of efficiency. So I want to finish this with a few last words. So the efficiency calculations suggest a roadmap for improving the efficiency of devices like the bionic leaf. We swap out carbon fixations for more efficient ones. H2-mediated systems might be difficult to scale up because of the low solubility of H2 in water. But there's a way forward. The thermodynamic maximum efficiency of these solid matrix nanowire systems and hydrogen are about the same, even though on the face of it they don't seem to be. And this means that it might be worth the effort to genetically engineer a sort of a nanowire-containing electroactive organism with carbon fixation and fuel synthesis that meets the demands of the synthetic biology design, build, test loop. Now, finally, one last thing. This is a plug. We didn't even get to rewired carbon fixation systems where CO2 is fixed electrochemically. And as a spoiler, You're going to have to wait for Farshid's paper, but as a spoiler, they do even better than biological carbon fixation systems. And with that, I'd like to say thank you and take some questions.
Well, as a spoiler, we're not going to take questions because I apologize. We need to stay on schedule.
I think I might have gone over with my enthusiasm, but thank you.
Quite all right, but you'll have a chance to ask Buzz questions at lunch if you want to follow up, and we'll move forward now. So let's give Buzz another hand for a great talk.
Thank you very much. Thank you.
Obviously, a lot of interest. So the next presentation is by John Hannon.